So the theorem we are going to prove is that if the RSA assumption holds, so if this is true, then our scheme pi is CPA secure under the random oracle model. So our proof will look like the following. If there exists a probabilistic polynomial time adversary A who breaks CPA security of the scheme pi, then we are going to construct another probabilistic polynomial time adversary B that has non-negligible advantage here in the RSA assumption. So it breaks the RSA assumption. And again, this needs to be done in the random oracle model, so B needs to simulate the random oracle for A. So let's start by defining our adversaries. So outside we will have the adversary B, inside we will have the adversary A. Adversary A is playing the CPA game for scheme pi. So the CPA game for scheme pi says the adversary must be given the security parameter together with the public key pk. And then the adversary can actually do the encryption queries himself, so there's no need for encryption oracle access. At some point, he will send us two messages, M0 and M1 from the message space. These messages are of the same length. We will respond with some CB that should be a ciphertext of one of these messages. And eventually, the adversary will output its guess for this B, which is some B prime. Remember, the adversary wins if this B prime is correctly guessing which message we encrypted here. On the other hand, what's the game B is playing? B is trying to break the RSA assumption. The RSA assumption says, so some challenger outside, we can call this challenger C if we want, runs this gen algorithm to obtain N, E, and D. The challenger also picks some X that is from Z and star. And the challenger gives to B the security parameter, so everything here, N, E, and X to the E. Okay, so these are given to B, and B's goal is to return X at the end. Now we have defined the games. Remember, since we are in the random oracle model, A also has access to the random oracle, and this can be anywhere. It can be here, okay, somewhere else, doesn't matter. So A will send some input Z to the random oracle, expects some Y back. So since we are in the random oracle model, this is part of the interaction with A. Now our goal is to write the code for B. So B's job initially is easy. Here it will send the same security parameter and it will set the public key using the values it received from its challenger as N and E. Remember, B is trying to tie its inputs to the adversary's inputs. Now the adversary sends two messages, M0 and M1. Normally, B needs to pick one of them. So let B pick one of them randomly. And then B needs to encrypt one of them, MB. How is the encryption working? Normally what B needs to do is, needs to pick a random value R from Z and star and to compute R to the power E. Now if B picks its own random value R and computes R to the power E, then we are not tying B's input to A's input. Instead, we have X to the power E already given to us for some random X. So what we are going to do is, we will set C1 as X to the power E that is given to us. So we are simulating C1 perfectly, but we are using the input given to us. Now we also need to simulate C2. For C2 we need random oracle of R, which is X here. Now we don't know X. Instead what we are going to do is we will pick Y randomly from the correct range, which is 0,1 to the length of the messages. And then we will compute C2 as Y XOR MB. And then eventually this CB will have two parts, C1 and C2. This is what we sent back. So given M1, M0, we do these sent back. Now here the interesting part comes. What if the adversary makes a random oracle query? So there are three options. The first option is the following. If Z is equal to X, then remember, random oracle of X needs to be this Y. So we return this black, so the green Y value as the black Y value. Okay? Now, otherwise, we have two options. As we do for a random oracle, we check that if we have already a Z-Y combination in our database, then what we do is we set this green Y we are going to send to the adversary as this Y value in our database. Otherwise, so if we still don't have anything related to the Z, so it's the first time we are seeing Z, then we pick a Y randomly from the correct range, which is 0,1 to the ln, the length of the messages. So we pick, let's say, a blue Y. We add to our database this ZY combination. So this ZY is added to our database, and this green Y we are sending to the adversary is computed as this Y. So whenever a random oracle query arrives, we had an initial database. What we do is we do this. Now there is one thing that's important here. Realize that this B does not know X. It only knows X to E model. So B cannot run this if condition. But what it can do is it can compute Z to the E and compare it with X to the E. B is given E, so it knows E. It can compute Z to the E given Z. It knows X to the E, so it can compare these. And remember, this comparison essentially means that Z and X are equivalent modulo N. So we are not losing anything important by changing this comparison. Now we are going to analyze the probabilities. So I believe you all agree that this will be polynomial time. There will be polynomially many queries here. There's no problem. These are simple things. All of them can be done in polynomial time. Now we need to analyze the probabilities. One thing we should realize is the following. This adversary is outputting a single bit, whereas our job is to output some Zn star element. So this is a much longer element, okay, around maybe 2 M bits. So given this 1 bit, these 2 M bits, our job is extremely hard here. We cannot convert this 1-bit information to 2n-bit information. So this is an interesting type of proof in the sense that the adversary's output here does not relate to our output here. And you can guess this because of their sizes. But instead, what happens is the following. There are two cases. Okay? Case 1. One of the queries of the adversary is a z such that z to the e is indeed equal to x to the e. So z to the e mod n is equal to x to the e mod n. If that's the case, what we do is we can output x as z modulo n. So essentially, if the adversary ever queries for such a z, then B manages to break the RSA assumption. So it manages to output the x value that is required for it. The second option is that there is never such a query z such that z to the e is equal to x to the e. Now, if A never queries for a z such that z to the e is equal to x to the e, or if it is easier for you to think, you can say A never queries for x, essentially. Then remember, A has no idea about this y. So if A never queries for x, essentially, it has no idea about y because y was chosen randomly. Now, when y is chosen randomly and A has no idea about y, this is exactly one-time path. So the probability that A wins, given that A never queries for, let's say, x, is exactly 1 over 2. We know this through perfect security of the one-time path. And the fact that for a random oracle, if A never queried the random oracle on that value, A has no idea about the corresponding output. So if A never queried, he can only win with probability 1 over 2. On the other hand, if A ever manages to query for, let's say, x, or essentially z to the e that is equivalent to x to the e, then B is breaking the RSA assumption. Now, what does it mean? If A has non-negligible probability of performing such a query, so if A has non-negligible probability of getting into case 1, then B will have non-negligible probability of returning the correct x. So B is going to break the RSA assumption with that non-negligible probability. If instead the RSA assumption, remember, we are assuming it holds, so B can only break it with negligible probability. This means A must only have negligible probability in getting into this first case, so sending such a query. So overall, remember, A wins if he manages to query, because if he manages to query for that, he gets the correct y and then can decrypt and figure out which B we used. So overall, the probability that A wins would be this 1 over 2 here, plus this value here. And if the RSA assumption holds, this value must be negligible. Therefore, we showed both ways. So for the theorem, we showed that if the RSA assumption holds in the random oracle, the A's advantage in breaking CPA security of the scheme must be 1/2 plus negligible. Again, thinking the other way around, if A had 1/2 plus non-negligible chance in total, since this part is 1/2, it means this part had to be non-negligible, which means B would have broken the RSA assumption with non-negligible probability. So it corresponds to the contrapositive. And now we are done with the whole proof. So it's not a standard style of proof that we are used to. This output has nothing to do with this output. But in terms of the probabilities, they are closely related. If A manages to make a random oracle query that is going to help him break the scheme, then we are going to break our underlying assumption. If A never makes such a random oracle query that can help him at all with breaking the scheme, then he wouldn't be able to break the scheme. And overall, that shows the security that we are trying to prove here.